Okay, go ahead.
Okay, so I'm not sure where to start, but here's what my my question for atheism. Atheists is that the arguments. I'll tell you. Why don't we start from the regular arguments, and then I'll lead you to where my arguments go.
Yeah.
Okay. So you don't believe in God, right? Some people argue and say, what about the creation of the universe? Right?
Okay, creation of the universe. Shall we start with that?
Yeah, start from the first cause.
Okay.
So why don't you believe in as a first?
So in terms of the first of all, I don't think there's any evidence the universe had a beginning.
Okay.
So
the universe could have been gone for.
It could have been. It's just been here forever. Okay. So now people have said there is evidence for a beginning in the Big Bang. Okay. But I think that's a misunderstanding of the Big Bang.
Why don't we address this one by one? So let's say, for example, so the universe didn't have a beginning. Okay.
No, I'm not saying it didn't. I'm saying we don't know whether it did. There's no convincing evidence that it did.
Okay. But I would argue but I'm just generally interested in science, so I don't mind having a discussion in general.
Yeah.
But I would argue that the universe does have to have a beginning because of the second law of thermodynamics.
Okay.
Because if it was for an infinite amount of time, right, then the entropy would be now by 1. Is it right? Is it? Yeah.
So the entropy would reach a maximal state.
Maximum state.
Yeah.
So it'd be complete.
So can I answer that?
Yes, please.
Okay. First off, you're assuming that the maximal entropy of the universe is a finite number. If the maximal entropy of the universe is an infinite number, then you can go forever. Okay? So there's an assumption built into the argument. There's another assumption built into the argument, or there's a mystery, if you like. Why was the entropy very low at the Big Bang? Okay? So it was very low at the Big Bang. I think there's no dispute about that. Okay? And
wait, we're talking about an infinite universe. Are you saying if there was a Big Bang? Okay.
There was a Big Bang. No, I'm not disputing that there was a Big Bang. But what I'm disputing is whether the Big Bang can be interpreted as the absolute beginning.
Oh, I see what you're saying. Okay.
So I'm not disputing there was a Big Bang. Absolutely, there was a Big Bang.
Okay.
I don't doubt that for a single second. Right. The evidence for that is overwhelming.
Okay, but the Big Bang it could have been just parts of many.
Yeah, part of a longer history.
Yeah.
Okay. So now what I do accept is that the entropy was very, very low at the Big Bang.
Yeah.
So the question is why? Why was it so low at the Big Bang? Okay. Now, we don't know is the answer. Okay. And it could have been that the dynamics of going from the pre-Big Bang universe to the post-Big Bang universe set the entropy to 0. And there are, I think, at least plausible theories in physics which will give you that. So, for example, when you say the entropy, what are you talking about? Do you mean the
so you've been filmed?
Yes. When you say the entropy, do you mean the entropy in matter or another entropy?
Well, I mean energy and matter. Yeah, I'm talking about energy.
What about the entropy in the gravitational field?
I don't know much about that.
Okay. So what we know is the entropy in matter would have actually been high at the Big Bang.
I would assume all entropies would work the same. That entropy
no. That's wrong. The entropy in matter must have been high at the Big Bang.
Must have been high?
Yeah, higher than it is today. Yeah.
Okay, why?
Because when we look at the cosmic microwave background, you're familiar with the cosmic microwave background, what you see is a thermal black body.
Okay.
Okay? Thermal black body is as high as entropy as you can get. Okay?
Not necessarily.
Yes.
There could have been distinctions within that.
But there are, but it's as close to a thermal black body as we've ever observed. So that's high entropy. So it's high entropy, it's not low entropy. So the low entropy must be, sorry?
Okay, so I'm not actually totally certain what a black body is. Is a black body, is that anything to do with infinity, like in the...
No, it's not anything to do with infinity. What it means is that when you radiate, it's not a function of its chemical composition. Okay. So
it's before the atoms were made. Is that what you mean?
Well, it doesn't have to be. I mean, it's not about when the atoms were made. It's about a thermal property of.
Is it the point that they're very, very hot?
It's not to do with the fact they're hot. It's to do with the fact that they're randomly configured. Yeah?
Oh, I see.
It's a configuration.
So how do you know that it's randomly configured?
Okay, so when we measure the proper thermal properties of the cosmic microwave background, you can compare it to the properties of a theoretical prediction of a black body. Okay. And what you find is an exact match. Okay, it's the closest match that we have. There are no closer matches anywhere in nature, anything that we observe. So the entropy in matter is high. So that means the entropy and gravitational field must have been low.
Is this accepted?
Yes, that's not controversial. That's not controversial at all. Okay, there are things I'm going to tell you which are controversial, but that is not one of them.
That's
okay, that's not one of them. Okay.
But
The
anyway,
entropy, the low entropy has to be in the gravitational field.
Okay.
Okay. So the question is, how does the gravitational field react if we go from a pre-Big Bang state to a post-Big Bang state?
Yeah.
Okay. And there are at least plausible models where the entropy of the gravitational field is killed off as you go from the pre-Big Bang to the post-Big Bang. So the entropy by itself cannot really be used as a proof of the beginning of the universe, because you don't really know if there was a pre-Big Bang universe, and there are many models of cosmology that say there was, how the entropy behaves as you go from the pre-Big Bang to the post-Big Bang. If it gets wiped out, as in some models, if it gets reset, then of course then you have an explanation for why the entropy was so low at the Big Bang in the gravitational field.
So whoa. How would it get reset?
Okay, so for example, I'll give you one model. Okay, and I'm not saying, and this is controversial. So there's some things I'll say are controversial, some are not. So the idea that the entropy of matter was high in the Big Bang, that's not controversial. Here is a model, and it's a controversial model, okay, but it will give you an explanation as to why the entropy was low at the Big Bang, or it was reset, if you like. So what happens is, where is the entropy in our universe? It's in black holes. Right?
Okay.
But that's just that is
I'm not familiar with that. No,
that's not
fine.
controversial.
I'm not familiar with that.
All the entropy in the universe is pretty much in black holes. Okay. Now the question is, what happens to black holes when?
You mean high entropy or low entropy?
High.
Okay.
So if you were to take all the entropy of the universe, almost all of it is in black holes. Okay. They're very high entropy objects.
Okay.
So if you were to add up all the entropy in the universe, you know, almost all of it would be in black holes. The entropy that's on the Earth is peanuts. It's nothing.
very low.
Yeah.
So are there really that many black holes?
Yes. There's a lot of black holes. Yeah.
So
and they have a lot of entropy.
And you're talking about the entropy of matter as opposed to energy, or both?
Okay, so what we're talking about is a distinction between the entropy in the matter fields and the gravitational fields.
Does matter include energy?
Matter and energy are interchangeable.
Right, that's what I'm saying. You mean both, matter and energy?
Okay, yeah, yes, okay. But we were trying to distinguish between the entropy of sort of the way the particles are configured and the entropy of the way the gravitational field is configured.
Right.
Okay, so if it's the case, so Roger Penrose, who is one of the top guys in relativity, he's proposed a model whereby what happens is you have black holes evaporate. That's not controversial. That pretty much everyone agrees black holes will evaporate. And what's controversial is what happens to the information when the black holes evaporate. Okay, so there's a debate about what happens to the information.
What do you mean by information?
Any way you could describe the configuration of the black hole. Okay. So if you throw the book has information.
But it could be the configuration of atoms.
So if you throw a book into a black hole, what happens to the information? Okay.
Right.
Now, general relativity would seem to imply that the information is destroyed, but quantum mechanics seems to say it's preserved, and there's a debate. And Roger Penrose takes the view that it's preserved, and we don't know who's right. I mean, there's just no way at the moment to definitively answer the question what happens to the information. Now, if the information is destroyed in the black holes, and you have a cyclic cosmology, then all the information, as the black holes evaporate, will be effectively gone. So the entropy will get reset. And what happens is you have something called a conformal transformation in his model. So to try and explain what that means is, so conformal geometry is a geometry of angles, irrespective of size. So if you take a statement, what do the angles of a triangle add up to? They add up to
180 degrees.
Yep, 180 degrees. And if you double the size of the triangle, it doesn't matter. It doesn't care. So we say that the angles of a triangle are conformally invariant. They don't care about scale. Okay. Now it can be the case that the whole universe becomes conformally invariant. It doesn't care about scale. And how might that be the case if there's no mass in the universe? If there's no mass in the universe, you can't build a ruler, you can't build a clock, so the scale of the universe becomes lost. So what Penrose argues is that at the Big Bang, there's no mass. The energy is too high, you can't form particles, so there'd be no mass. And he controversially asserts that in the far future matter will decay away. Now that's controversial. There's less controversy about the no mass in the early universe, and more controversy in the far future. But if that were to happen, right, then you can get this conformal transformation, and you get this cyclic cosmology. And what you find...
If atoms disappear.
Yeah.
Okay. Or turn into energy.
Yeah, they just have to turn into energy, yeah. Then you have this conformal invariance. Now what you do is you look at the Einstein equations of this, and you look at how gravity propagates through the crossover, and what you find is the entropy will be killed off, and it'll be reset to zero every time you go from pre-Big Bang to post-Big Bang.
So are you saying the entropy would start over again because the particles are being destroyed and turning to energy?
Yeah, and it's also the dynamics of the crossover and the conformal transformations. But basically, it's like the entropy.
And what are you basing that on? Is that based on the understanding of what that energy is like, or is that
it's based off?
Assumption?
It's not just an assumption. There are some controversial assumptions. There's two controversial assumptions in this model. Okay, one is that information is destroyed in a black hole, and that we just don't know if that's true or not. Okay. The relativity, a theory of relativity, developed by Einstein, says that information is destroyed in a black hole. Unfortunately, the other theory that Einstein helped to follow, quantum mechanics, says it will be preserved. And there's a conflict, and we don't know how to resolve this conflict. Okay. So it's legitimate to argue for either case, in my opinion. Okay? We just don't know which is true. Okay? Now, I have to say, most physicists will say the information is preserved. Okay? But there's no proof of that. And in fact, they thought they had some proof, and now it's come undone. Okay. Right? So there's certainly, I think, and the other controversial assumption is that energy will decay away in the far future. Okay? But if that were to be the case, then you could get, if you like, the entropy to be reset. And there are other ways that you could get the entropy to be reset as well. It's all about the general point I want to make is not to hang everything on Roger Penrose's controversial model. The point is that we don't really understand what happens at the Big Bang. And therefore we can't rule out models like this where the entropy gets reset as you go from a pre-Big Bang universe to a post-Big Bang universe. And therefore to argue that the universe cannot be eternal in the past because of entropy, I think is an illegitimate argument.
Okay. Here's the thing. I would say that if you accept in order to say that the universe had an infinite was there for infinity, would you agree? I think you agreed, but maybe not so clear.
Yeah.
Would you agree that the laws of entropy don't have to always apply? Because if you're resetting them, that means they don't always apply.
No, the laws always apply.
But if it's being reset, how does that?
Because it doesn't conflict with the laws. You have to understand the detailed nature of the law. And Penrose, I've interviewed Penrose and he's explained this, and he's very clear this does not conflict with the second law of thermodynamics. There's no conflict at all. You just have to include in the way you analyse the law and its implications how you define the entropy. And what happens is you have to rechange the way that you count. It's about state counting.
Sorry. So the entropy resetting, how's that not breaking the second law?
Yeah, that's
okay. Because the second law doesn't really say that entropy always increases. That's just a generalization of the second law. But when you look in the real detail, that's not exactly what it says. Okay, what it says is that given a certain configuration of atoms, okay, or particles, that a macro arrangement of those atoms will have a certain configuration. It will explore a certain configuration space. So let me try and explain this with an analogy, right? Probably I'm not being very clear with my words here. So let's suppose you have a brick wall made of Lego bricks, and you can arrange them with different coloured bricks and you make a face. Okay? That we would consider a low entropy state. There's more ways for it not to be a face than to be a face. Okay? And that's what we mean. So when you rearrange these Lego bricks, yeah, you find that pretty much every rearrangement that you make will increase the entropy. Okay?
Any random? You mean any?
Yeah. If you randomly juggled the bricks up, yeah. But it all depends on how many bricks you've got and what the possible configuration space of the bricks is. And what the argument would be is the actual allowed configuration space as you go through the pre-Big Bang to the post-Big Bang would be such that you could get automatically a low entropy state at the Big Bang. There's other ways you can define entropy as observer dependent. So you can say, for example, that I count how many states there are, of macro states there are associated with a given microstate. Yeah, how many ways there are to make the face, given how many bricks I have. So basically what you say is it's a number of macrostates associated with a certain number of microstates, and it's all about, therefore, what we call state counting. And some physicists have argued that really you understand the laws of thermodynamics are effectively observer dependent.
Sorry, I just want to clarify. So, for example, if you had three digits, right?
Yeah.
So that would be 1,000 macrostates.
So
something like that.
that would be a reasonable analogy. Yeah. So the question would be, there could be dynamics going through the post-Big Bang, pre-Big Bang to the post-Big Bang that automatically put the configuration state into a low entropy state, and that would not violate the laws of thermodynamics at all.
No, of course.
Yeah.
That's why personally I have some problem, believing the second law of thermodynamics. There's a very good guy, what's it called? Susskind?
Leonard Susskind, yeah.
Leonard Susskind on YouTube. He explains this with the
with the coins. It's a very good explanation of thermodynamics. And in fact, he's got a point that really disproves, at least by itself, the notion that entropy can prove the universe has a beginning. Because there's another theory, not just second law, there's another theory called Poincare recurrence. Poincare recurrence. It says that any configuration space will always return to its original starting point if you give it enough time.
Of course.
I just want to focus.
Yeah.
Sorry, it's all about God, really.
Sure.
I mean, it's both.
But of course, you're trying to establish that the universe must have had a beginning. And I'm saying...
I'm not actually.
Oh, okay, sorry, I thought that was what you were doing.
No. That was kind of sidetracked because I don't.
But then why did you raise it?
Well, two reasons. Number one, I'm interested in the science.
Okay.
And number two, because I think that if you have many different things, that you have to decide which one I'm going to prove it from. I have to see where we stand.
Yeah, of course.
And also, I thought that was wrong, so that's why I want to discuss it. Here's my general point.
Yeah.
Right?
Okay.
This is the way I see the whole understanding of the argument. So I'm going to go. I wouldn't say philosophy, but kind of a little bit.
Yeah.
So what the way I see it is that, take for example, classical mechanics. Yeah. So classical mechanics break down the quantum level, right?
Yeah. Sure.
Okay.
Sure.
So when you're talking about, the way an atheist will see the world, I'm simplifying things.
That's fine.
We'll say that it doesn't believe in God because the universe goes according to natural laws. We don't need a God because there's natural laws and the universe runs according to that. We don't need no God.
Well, my view is I'm an atheist because I don't see evidence for God. It's not because there are natural laws.
Okay, that's what I'm
I don't see. I think the arguments that have been proposed for God don't work. Therefore, I don't believe.
Okay, but if there could not be natural laws, right? You know what? Just go according to my way. We'll deal with it later.
Sure.
Okay, so what I would say is that in science, right? Classical physics breaks down the quantum level. So the laws that we believed were true, that were governing the universe, right? Before quantum mechanics, turn out to be not laws at all, but rather.
Well, they're approximations. I mean, I think all laws are approximations.
Well,
and we found in quantum mechanics a better approximation.
They are laws in the sense that the universe functions that way. They are not laws in the sense that the universe has to function that way. Right? Is that acceptable? Because on the quantum level,
I just think we don't know what has to be. We only can say what is.
Well, we do know. Okay, according to science, right? Before there was matter, there didn't have to be matter, right? Because there wasn't. That's the proof that it doesn't have to be.
Okay, that's fair. Yeah, okay.
Right,
But whether the laws have to be as they are, that we don't know. Well, so I agree. Yes, matter doesn't have to exist. I agree with that.
Well, the laws only function. It tells you how something works. But if something doesn't exist, then obviously it doesn't work.
Well, that's a debate. What is the ontological status of laws? Are they effectively commands that objects have to obey, or are they just descriptions of the way objects behave? And I think we just don't know the answer to that question. There are some philosophers that would argue, and physicists that argue, no, the laws actually have their own ontological status, a bit like Platonic mathematics.
Right.
So we don't know. I think we don't know what the answer to that question is.
But I mean, I would argue, right, that because since there was a time where these laws didn't apply, right, because there was no matter, so you couldn't have.
No, but that wouldn't mean the laws don't exist. I mean, if the laws of physics have their own ontological statements, I mean, our laws, classical mechanics, we could describe as a law of physics, and quantum, they're approximations, we think, to the real laws that govern the universe.
Right? That's what I'm getting to.
So the question is, what is the ontological status of those laws? Whatever our descriptions are approximations, but if there's some ultimate, I mean, hopefully there's some level where the laws of physics that we understand cannot be approximated anymore. They are just exact, right? That's how things behave.
Okay.
Okay, now the question is, do those laws, could they be changed? Could we have different laws? And I think we just don't know. Maybe we could, maybe we couldn't. We don't know.
Would you accept that analogy of a computer would work for the universe? So, for example, if you make a program, right, and the program works in a certain way, you can say those are laws of program. When you press A and A comes up on the screen, that's a law of the Microsoft Word or any program that you're using, right?
Okay, yeah,
so,
sure.
would you say that analogy works for the universe in the sense that if it's made in this way, and therefore the laws are just a reflection of the way things are made? I
think there's more mystery about the nature of the laws of physics than there are about the operations of a computer.
Okay.
You know, I mean, although of course the computer reflects the laws of physics, so in a deeper sense they're the same thing. But what I'm saying, so I think there's a sense where the analogy breaks down in that we know, for example, that you could change to a different computer language. We don't know that the laws of physics could change to a different set of laws. So we don't. So let's say E equals mc squared, just as the most famous equation. Could it be the case that E equals mc cubed? Could that be possible? Well, we just don't know. Maybe it cannot be. Maybe it could be. Maybe there's another universe where E equals mc cubed. Maybe that's impossible. Maybe it's just has to be E equals mc squared. And I think we don't know which of those two is the case.
Okay, but I mean, look. Here's the thing. If you take, for example, gravitational pull on the world, right?
Yeah.
If you only lived on the world, right, you would say 9.8 gravitation. That's a global law, right?
Yeah.
Then you go to other planets, you find out it's not a global law. There's a general gravitational law, right?
Course.
So it's not fixed.
Yes,
it just depends on the situation.
Exactly.
So it's like a computer. If you have this situation, then that's.
But we don't know whether that's true of the laws of physics or not. It might be true.
No. But what I'm saying,
it might be true.
I'm saying you're agreeing with me that it depends on the situation. It's not that law of 9.8 gravitation is not a law.
Right, but if you
it's not a total law. Okay. It's just relative to
if you take
this Earth. So if you had a different universe, you could have different laws, right?
Well, maybe you could, maybe you couldn't. We just don't know. It's certainly a plausible
would you say
statement.
It's reasonable?
Yes,
is it reasonable?
I think it's a plausible statement that with a different universe, and there may be other universes. I think there's some evidence that there are other universes. It's not overwhelming evidence, but I think there's some suggestions from physics that there are other universes, and I think it's completely plausible that they would have other laws of physics. But we don't know that, and we can't assume.
I don't know that because I'm not good enough at physics. But
no one knows. It doesn't matter how good you are at physics. Nobody knows whether the laws of physics could be different. I think it's a plausible thing to suggest that they could be different, but we really don't know.
We don't know. But here's the thing. The way my understanding of the universe is that these laws break down, right? So at any stage, right? So you've got classical laws, you've got quantum mechanical laws, and there could be laws below that. And
there could be deeper laws than that. I think there probably are. Yeah.
So there's no reason to believe, right, that there's any laws that exist totally, right?
Oh, well, no, I don't agree with that. I mean,
if laws keep breaking down as you go to a lower level, right? Doesn't that point to the idea that eventually there's no laws?
I don't think you can conclude that. I think there could be some description of the universe where you can't go any deeper. That's just it. This describes everything, and that could be the case. I mean, we don't know. We only know the laws that we know and how good an approximations they are, and they are very good approximations. There's very few cases where the laws of physics, as we understand them, don't apply, or we think don't apply, or are in conflict in some way. It's only really very extreme cases, like at the centre of a black hole or the Big Bang, where we think the laws that we understand them probably do break down. But that doesn't mean that there isn't some deeper theory where they don't break down, and maybe there is some deeper theory where they never break down.
So I think we don't know.
Okay,
so let's say we don't know.
Yeah.
Right?